Alright, so let's see what happens here. Now, did anybody graph it to see if it actually has an inverse before they went to all the trouble of, solving for it? That's true. All the powers are odd, so that's a good sign. You just went for it. You boldly began solving. Let's go ahead and graph it, just to see. So does this actually pass the horizontal line test? And I still have my old inverse graphs. Go back up. Okay. So does this actually pass the horizontal line test? It looks like it does, right? And it's got a horizontal asymptote at 1 over 1. At 1. At x equals 1. Y. Okay. So then let's try this. So h of x, we're going to put our y there, only we're going to switch the x and the y. So you'll probably, like I'm doing right now, skip through that first step of rewriting it and just jump straight to switching the x and the y. Okay, now we've got to solve for y. And just like the last problem, the main issue here, two main issues, we have two different y's. And one of them is on the bottom of a fraction. That's not a good spot for it if we're going to get it by itself. So let's take care of this fraction. Let's not have a fraction anymore. What should I do? Yeah, you could cross multiply. That's essentially what we accomplish by multiplying each side by y minus 1, right? So you end up with the same thing. And I'm going to go ahead and distribute over here. So that's going to be x times y minus x equals, and on the other side, y plus 3. Okay. So one problem solved. We don't have a y on the bottom of a fraction anymore. That's good. But we still have too many y's. There's one over here, there's one over there. I want to put those y's together. What should I do next? So I need to move the y over. Now you said add the x. I'm gonna save that for the next step just to make that clear, in case anybody didn't catch that. That says minus y, by the way, equals 3. Okay. So what happens if I try and factor out a y here? Okay. So that's why you're telling me I need to add the x over to the other side? Okay. So I've got xy minus y equals 3 plus x. So essentially what I'm going to do here, or what I just did, is I'm going to separate my y's from my non-y's. Anything that has a y, I'm going to put it on one side. Anything that doesn't have a y, put it on the other side. And that way, we'll be able to factor out that y as a common factor. So y times what? X minus 1. Now we have a single y. So that's what we have to do when we have more than one copy of a variable, at least if they all have the same power. So put them all on one side, and then factor it out. And then last step, divide by x minus 1. And I should probably answer the phone, but there's my inverse. Do you notice anything? Okay, so did you notice anything? Oh, hi. Still on video. So what was this? This was h of x, right? So h inverse of x is 3 plus x. over x minus 1. What was the original equation? Huh. That's the same thing, isn't it? What? No? Oh, yes. So, should I graph the inverse to see what it looks like? Well, I kind of already did, didn't I? Because I graphed the original equation. So, is there anything on the original equation on the graph that might have tipped you off that this function was going to end up being essentially its own inverse? Probably. So what did we say we should see when we graph the function and its inverse on our graph? Hint, it's a type of symmetry. Yeah, y equals x symmetry. So a function should have y equals x symmetry with its inverse. What about this function? It has y equals x symmetry with itself. You see it? It just has y equals x symmetry by itself. Therefore, it is its own inverse. Do you remember how we tested for y equals x symmetry? I know that was a long time ago. We switched the x and the y, and then we solved for y and see if it was the same as the original equation. Hey, look. It's the same as the original equation. Okay, so if a graph has y equals x symmetry, then it's going to be its own inverse. Fun fact. You might want to jot that down in your notes. Yes.